Alright, this is the third video for Chapter 8, looking at chemical equations, how to describe chemical reactions that take place. So in this video, we're going to talk about what kind of information those balanced chemical equations with those coefficients, what information it actually gives us. And then after that, we're going to talk about some different types of chemical equations. So let's look at an example equation. Alright, this is an example of a combustion reaction, by the way. Whenever you have a compound or a molecule that's a hydrocarbon, like propane, C3H8, it's an organic hydrocarbon compound. Whenever these hydrocarbons, if you ever see them react with oxygen, okay, they will combust to form carbon dioxide and water. So whatever hydrocarbon you use, if you get a complete combustion, you're always going to get carbon dioxide and water out as products. An example would be like octane in your car, the main component in your fuel. Octane combusts when it reacts with oxygen, and what comes out the tailpipe there? Carbon dioxide and water vapor. So propane, the propane tanks like in your fireplace or in the grill, if you have a propane tank, same thing. Your byproducts of the combustion are carbon dioxide and water. So this is the type of reaction we're looking at. Combustion's not so important, but I just wanted you to know what the reaction was. So here we have propane, and in this reaction it says we're given the balanced chemical equation. So one molecule of propane reacts with 5 molecules of oxygen, and for every one of those combustions, 1 to 5 propane to oxygen, it will produce 3 molecules of carbon dioxide and 4 molecules of water. So that's, in general, how most people, after we've balanced the equation, would read that chemical equation. They would read it on the molecular level. 1 propane plus 5 oxygens yields 3 carbon dioxides and 4 waters. But what we've seen since we've balanced the equation is that you can look further into the equation to gain information about the atoms involved. For instance, we know that propane contains carbon and hydrogen, but because we know the formula of propane and how many propanes we have, we can see how many carbons and hydrogens are reacting. We have 3 carbon atoms and 8 hydrogen atoms reacting with how many oxygen atoms? 5 times 2, or 10 oxygen atoms, to produce 3 carbon dioxides, which is 3 carbon atoms, and 3 times 2, or 6 oxygen atoms, and 4 water molecules, or 8 hydrogens and 4 oxygen atoms. So when we look at the chemical equation as chemists, we not only see the molecules, but we also see the atoms that are bonding in the molecules and how many of each there are, the ratios. I'm going to tell you now about a third way that we can read these reactions. Instead of reading them on the molecular scale, chemists often read on the mole scale. Now, what is a mole? Remember, a mole is a unit of something. It's 6.022 times 10 to the 23rd of anything, that Avogadro's number. What if I asked you, by the way, let's just look at this on the molecular scale again. If you have 1 molecule of propane, you would say you need 5 molecules of oxygen, looking at the reaction, in order to produce your carbon dioxide and water correctly. That's the stoichiometry would say, or it's the balanced chemical equation with the coefficients of how much of each you would need. What if I asked you to increase the amount of carbon dioxide and water you made by 12? What if I say, think about this as a dozen? What is a dozen? It's just a unit that means a number, right? A dozen of anything is 12. So on the molecular level, instead of reading 1 molecule of propane, if I asked for you to read this on the dozen scale, you would say 1 dozen propanes plus 5 dozen oxygens yields 3 dozen carbon dioxides and 4 dozen waters. You would just multiply everything times a dozen, or 12, right? Well, the same thing can be done for a chemical reaction on the mole unit scale. If I asked you to increase from the molecular level, 1 molecule, up to a mole scale, that would be make saying multiply everything times 6.022 times 10 to the 23rd. instead of saying that number forever, why don't we just use the word mole? Kind of like instead of saying 12 propanes, just say a dozen propanes. When we reread this reaction, if we substitute the unit mole in, we can read on the large scale. So I'm going to try it again. I'm going to read the equation with its balanced coefficients using the mole scale. So instead of 1 molecule of propane, we would say 1 mole of propane plus 5 moles of oxygen yields 3 moles of carbon dioxide plus 4 moles of water. So for each atom, we multiply it times Avogadro's number, and we have that many molecules. So that one's pretty easy now. I think you can understand. We can read on the mole level. Generally, when a chemist reads a chemical reaction, in order to perform a chemical experiment, like in the lab, when we have to use amounts of reagent we can actually handle and see, we're not going to go in and we're not going to read this recipe as, oh, I'm going to go find 1 molecule of propane. I'm going to go get 5 molecules of oxygen. That's very difficult. We can't actually do that. I can't take my little molecular tweezers and find my 5 moles of oxygen. 5 atoms of oxygen. But what I can do is I can quantitatively figure out a way to get a mole of propane and 5 moles of oxygen. And that will give me something tangible that I can hold and work with. So most chemists, when they do chemical reactions, we do work on the mole scale. Now, when you go in the lab, if I asked you to do this chemical reaction, if I told you to go get a mole of propane, would you know what you were doing? Oh yeah, let me go over to the mole scale and weigh out a mole of propane. You wouldn't be able to do that. Although chemists count in a mole, it's the unit that we usually count by on the large scale, it's not the unit we measure by. Remember in Chapter 7, we said that chemists count moles using mass. So we can calculate something called the molar mass of a compound. So for instance, instead of saying a mole of propane, if I asked you to go get a mole of propane, by the way, you would say, well, in order to count that out, I'm going to have to weigh it. How much does a mole of propane weigh? Well, 1 mole of propane has 3 carbons plus 8 hydrogens. My screen's giving me issues here. I just want to write hydrogen. All right, so 3 carbons plus 8 hydrogens. Well, how much does a mole of carbon atoms weigh? Well, 1 mole of carbon atoms weighs 12.01 grams per mole. That's the molar mass of carbon. Remember doing that? And if we have 8 hydrogens, we know that each hydrogen, if you look on the periodic table at the average mass, that's the molar mass, each hydrogen atom weighs 1.01 grams. So if we multiply 12 times 3, oh wait, what did I do there? 12 times 3 is 36. And then we have 8 times 1, so roughly 8. 36 plus 8 equals about 44 grams per mole. Remember calculating the molar mass of a substance? That's exactly how we did it. Now, I'm not using correct decimals there, but you can see that we can calculate a mole by its molar mass. So if I say that I have 1 propane, as a chemist I'm going to see that as 1 mole of propane, and I would use the molar mass. 1 mole is 44.90 grams. So if I was going to do this reaction, I'd go get 44.09 grams of propane out. And there's tricks, because it's a gas in a tank, there's tricks how chemists do that. But that's how much I would weigh out. What about the oxygen? There's 5 moles of oxygen you're going to need. Well, we're going to figure out how much a mole of oxygen weighs and multiply it times 5. So oxygen's O2. An oxygen atom weighs 16 grams per mole, but there's 2 of them in one molecule. So O2 weighs 16 times 2, or 32 grams per mole. That's the molar mass of oxygen. But how many moles of oxygen do we need? That's per mole. We need 5. So what's 32 times 5? 160. So if I was going to go get 5 moles of oxygen gas, I would go weigh out 160 grams. See that? What about carbon dioxide and water? Same thing. we have 3 moles of carbon dioxide. So 3 times the molar mass of carbon dioxide will give us the weight of the carbon dioxide we need. Water weighs 18.02 grams per mole, but we need 4 moles of water, so we're going to get 72. So another way that a chemist looks at a chemical equation is by the mole scale. So we read the coefficients as mole quantities. And then we can use the molar masses to determine how many of each reagent we're going to combine in our chemical reaction and how much we would get out weight-wise. So we're going to be looking more into quantifying and predicting, like as a chemist, what if I added a certain quantity of propane and a certain quantity of oxygen together? Could I predict how much product I could make? It turns out because we've got the recipe or the chemical equation, we can actually predict how much of each product we would make, mass-wise or by mole, because we've got a balanced chemical equation. We're going to do that in Chapter 9. So just understand how to read the equation for now. When we get to Chapter 9, we're going to start doing calculations with these recipes or these chemical equations. For now, though, we're going to move on to talking about types of chemical equations. So now that we know how to balance a chemical equation, the law of the conservation of mass, we're not going to destroy the atoms, we're just going to rearrange the bonds. And we also know how to read the balanced chemical equations, the different ways chemists use those. Now we're going to look at different types of chemical equations we're going to encounter. And in this class, we're going to encounter basically 4 different types of chemical equations. Now in general, equations are always reactants go to products. So what do I mean by types of equations? We're going to see that sometimes, just by looking at what types of reactions we have, we can understand a little bit more about what's happening with the atoms. So we're going to classify chemical equations in this class in 4 different areas. Either combination reactions, decomposition reactions, single replacement reactions, or double replacement reactions. Now we're going to look at these quickly, and then we're going to go and look at them in more detail. So what does a combination reaction mean to you? Those words, combination. Well, I see the word combine in there. When 2 or more substances combine to make a larger substance, you have a combination reaction. So the simplest type would be if 2 different substances combine. So if you have substance A, could be like hydrogen, and you have substance B, maybe it's oxygen. If those 2 substances combine to make a compound AB, instead of being separate, then you have a combination reaction. So we saw in a reaction earlier, it was hydrogen plus oxygen. When you added heat, it made water vapor. That was an example of a combination reaction. 2 elements combined to make one compound. Does it always have to be just 2 elements? No. It could be 2 or more elements combined. But whenever you start with more reagents on the left and you end up with less reagents on the right, that means some of those reagents have combined. All right? Let's look at the different type. The next type is a decomposition reaction. Now, what did decomposition mean? Decompose meant to break something from a more complex substance down into its simpler parts. So basically, it's the opposite of a combination reaction. So a decomposition reaction would be the opposite of the reaction above. If you have a compound or a more complex substance, if it breaks down to produce more pieces of simpler substances, so AB going to, let's say, A plus B, or maybe water reacting to form hydrogen plus oxygen, that's an example of a decomposition reaction. Okay, the next type of reaction is called the single displacement reaction. It's also in some books called a single replacement reaction. Displacement and replacement, it's going to be the same thing depending on the book you look at. Okay, but what's a single displacement reaction? If I have element A and I react it with a compound that contains elements B and C. Okay, so I've got A, pure substance, plus BC, a compound. If they react, a single displacement reaction would be when A substitutes or switches places with one of the elements in that reaction, or that compound. So maybe if it replaces B, B would come out as the element, and A would then be combined with C. So they exchange places. It's like exchanging partners in a dance or something. Now A could also, by the way, instead of replacing the first element, sometimes A could replace the second element as well. So what if it replaced A with C? If they switched places, you would get a different reaction out. You could also say A plus BC yields C plus BA. Alright, so that's just an example showing you don't always have to substitute the first reagent. You can substitute any reagent in that compound or element. Alright, and the last one we looked at is called a double displacement reaction. We're going to look into these in more detail, obviously. There's no reagents A, B, and C. We're going to look at specific examples. But what's a double displacement? Well, instead of one atom switching with another atom, it's two atoms switching places. So here we're going to be looking at two compounds. Compound AB plus compound BC react. And basically, it's kind of like two couples dancing, and someone says switch partners. Like, I'm from Kentucky, so we have hoedowns, so we're always switching partners. But that's kind of what's happening here. It's kind of like a molecular hoedown or something. Two of the atoms are going to be switching places. And we'll talk more about it later, but usually it's the first atoms switching places with the second atoms. So if A and B, oops, why did I put BC? Somebody stop me. I'm crazy. If A plus B reacts with CD, let's just do that. It'll be less confusing. If atoms A and C switch places, now C will be combined with B, and A will be combined with D. Alright, so that's a double displacement reaction. Okay, now, as far as combination reactions go, we're going to look at a few examples here. At this stage in the game, I don't need you to be able to predict the products of the reactions. For many of the reactions that are combination reactions, the products are very predictable. But at this stage in the game, I just want you to be able to recognize that something is a combination reaction. So if I give you an example reaction, you could recognize that it was a combination reaction. So let's look at the different types. Sometimes you can combine metals with oxygen, for example. And this is a very famous reaction because it occurs all the time in nature. Have you ever heard of something called an ore? An ore is a metal oxide. And we have iron ores, we have tin ores, we have just all metal ores on the earth that we actually collect and we refine, and we actually will refine them back into the pure metal. So like all of the iron you get is usually from iron ores found in nature on the earth. How is that produced? Well, when you have an unstable metal, and that metal reacts with oxygen, like in the atmosphere, they will combine to form a metal oxide. So magnesium plus oxygen yields magnesium oxide. What I want you to be able to see out of this is that in this reaction, can you tell that you're combining things to produce a more complex product? Yeah. Here we have the backbone A plus B equals AB. So if in this example, can you see that we have A is magnesium, the element, and it reacts with B, which is oxygen element, and it produces the ionic compound magnesium oxide. Alright, so we have A and B. We have two things on the left side, and we can reduce the number of things on the product side, so we're combining them. Alright, we can also do this with nonmetals as well. Nonmetals will also react with oxygen. So in this case, the example is nitrogen plus oxygen yields dinitrogen monoxide. So once again, we have two reactants combine, or they react and the elements rearrange to bond together to produce one compound. So they're combining. It's a combination reaction. We also see this in the formation of salts. Remember, the salt is basically a simple word for an ionic compound, and simple ionic compounds are formed from metals reacting with nonmetals. So in this chemical equation here, we've got a metal, aluminum, reacting with the element, the nonmetal, bromine, and when they combine, remember they exchange electrons, they ionize one another, there's an electron transfer, and they produce the ionic compound, aluminum bromide. So once again, do you see that this is a combination reaction? We have two things on the left. They're combining to form one product on the right, an ionic compound. All right. We have other examples here where we make metal bases, metal hydroxides, and we can make oxyacids. But once again, we've got two things combining to make one more complex compound. Two compounds combining to make one compound. So all of these, you've got multiple elements or compounds combining to make one larger and more complex compound. Combination reactions. Be able to recognize those. Alright, so we said the second type of reaction that we're going to look at, or we were looking at, was a decomposition reaction. And we said this is where one substance will decompose or break apart to form multiple smaller pieces. So all the pieces that were part of that complex substance become part of the smaller pieces in the product. So once again, for these reactions, I just want you to be able to recognize that you have a decomposition reaction. So an example here, we've got mercury 2 oxide reacts to form mercury plus oxygen. Notice that our reactant is just one ionic compound, and our product is two elements. So can you see here that it's decomposed or breaking apart into simpler substances? Yeah, the elements in this case. Here's another example. Here we have a metal carbonate. It's a sodium carbonate. Sodium carbonate can decompose or break apart to form, so we have one substance breaking apart to form the metal oxide, sodium oxide, and carbon dioxide. So once again, we have one substance breaking apart into smaller pieces. Okay. Another example here. This example, we have sodium bicarbonate. We only have one reactant again, and that reactant breaks apart to form how many products? In this case, it's 3 pieces. So we start with 1 and it breaks apart into 3. That sodium bicarbonate forms sodium carbonate, carbon dioxide, and water. We're decomposing it into smaller portions. So these are examples. It's the opposite of a combination. It's a decomposition reaction. Now we're going to explore the next 2 reactions in more detail in the next video. Single displacement reactions and double displacement, because I would actually like you to be able to predict those products. But for the composition or combination and decomposition, I'd just like you to basically, if I give you a reaction, you could tell me what type it was, of reaction it was.